You've heard that it's impossible to send information faster than the speed of light because physics? Yes, I've heard that too, but I think it's wrong. And in this video, I want to explain why. Is it possible to break the speed of light limit? That's what we'll talk about today. If you've been following this channel for a really long time, first of all, thank you. I know it isn't always easy. Second, you may remember that I already made a video about faster than light travel a few years ago, but I think no one understood it. In fact, when I watched it again recently, I didn't understand it either. So please give me a second chance, because I think it's becoming increasingly relevant to get this right. And this time, I'll try to do it better. I'll even let you leave the toilet seat up. In the past year or so, there's been a lot of talk about unexplained aerial phenomena, formerly known as UFOs. I don't actually believe any of those are of extraterrestrial origin, because as I said, we're just too boring for aliens to bother visiting us. Then again, what do I know? Maybe some of those aerial phenomena really are space probes from alien species. And if we want to properly evaluate how likely that is, we need to talk about the possibility of traveling faster than light, or at least sending information faster than light. Because
Actually, I'm just going to use my mic to say this. A lot of people say, oh, Earth is too boring for aliens to visit. We won't have any aliens here. But what I think is, like, we send space probes to asteroids and so on, and all these moons, ice and rock moons, they're exactly the same as each other. We send probes to those, so why wouldn't aliens send probes to Earth? I mean, that's assuming they even know it's here before they send a probe there. Like, I imagine an alien space program might just, like, throw probes at stars, just everywhere they can if they have the ability to, so, just avoiding a planet with life and such, it just seems kind of a weird explanation to me. I think if aliens aren't here, then it's just because they can't get here. Wait, have I already said this point before one? If I've already said this in response to a video at some other point, let me know. I feel like I've said something like this before. That's weird. Anyway.
if it's possible at all, then that's what the aliens are doing. The idea that the speed of light is a limit comes from Albert Einstein's theory of special relativity. Yes, this guy again. The speed of light plays a special role in his theory because it's the only speed that's the same for all observers. And just to make sure, I mean the speed of light in vacuum. The speed of light in a medium, any medium, is slower than the speed of light in vacuum, and it depends on how you move relative to the medium. But the speed of light in vacuum does not depend on how fast you move, because there's nothing for you to move relative to. I know this sounds about as exciting as flossing teeth, but it has some unexpected consequences, and I don't mean that your crowns pop off. Suppose you and your friend, let's call him Bob, both have a water hose, and it spits out water at, say, 10 kilometers per hour. Bob gets on a train which moves. And just to make sure, I mean the speed of light in vacuum. The speed of light in a medium, any medium, is slower than the speed of light in vacuum, and it depends on how you move relative to the medium. But the speed of light in vacuum does not depend on how fast you move, because there's nothing for you to move relative to. I know this sounds about as exciting as flossing teeth, but it has some unexpected consequences, and I don't mean that your crowns pop off. Suppose you and your friend, let's call him Bob, both have a flight in vacuum does not depend on how fast you move, because there's nothing for you to move relative to. I know this sounds about as exciting as flossing teeth, but it has some unexpected consequences, and I don't mean that your crowns pop off. Suppose you and your friend, let's call him Bob, both have a water hose, and it spits out water at, say, 10 kilometers per hour. Bob gets on a train which moves at 200 kilometers per hour. If you live in the United States, make that 20. Then he turns on his water hose again. The water moves with 10 kilometers per hour relative to him. But how fast does it move relative to you? You'd expect it to be the speed of the water plus the speed of the train, right? Now imagine you don't have water hoses, but laser pointers. They send out light with, well, the speed of light. Your friend Bob gets on a train again, in vacuum, of course, because this is theoretical physics where people don't breathe, cows are spheres, and 3 is either equal to pi or infinity, depending on who you ask. How fast do you see the light of Bob's laser? You'd expect this to be faster than the light that comes out of your laser pointer by the speed of the train, but not so. It moves with the exact same speed as yours, because the speed of light is always the same. This is what was confirmed with the famous Michelson-Morley experiment, and it has a very odd consequence. You can't catch up with light. It doesn't matter how fast the train is, light will still move away from it with the speed of light. If that didn't make your crowns pop off, you've probably heard it so many times before that you've forgotten how remarkable it is. That, or you have a very good dentist. We can quantify the difficulty of catching up with light by asking how much energy it takes to accelerate an object. Let's suppose the object has a mass m. This mass corresponds to an energy which is given by the most famous equation ever, E equals mc squared, where E is the energy and c is the speed of light. But now we accelerate this massive object from zero velocity to some other velocity, v. The energy you need for this acceleration is the total energy of the object at the new velocity minus the energy it previously had. In Einstein's theory, the total energy of an object that moves relative to you with velocity v is given by this expression. Now, if you want to know the kinetic energy, you take this and subtract the same expression for zero velocity. So you get this somewhat somewhat messy expression, but don't despair, it isn't as bad as it looks. For one thing, when the velocity v is much smaller than the speed of light, then the ratio v over c is much smaller than 1. In this case, the complicated thing with the square root is approximately 1 plus 1/2 v over c square. The 1 cancels out and the c's cancels out, and you get 1/2 mv square, which you might remember is just the kinetic energy. But we're more interested in the case where the velocity gets close to the speed of light, so v over c gets close to 1. Then this factor gets close to 0, and the entire energy gets close to 1 over 0, which is infinity. This means if you want to accelerate an object until it reaches the speed of light, you need an infinite amount of energy. Another way to put this is that the only way you can move at the speed of light is when your mass is 0. Even a keto diet isn't going to do that for you. This is where the idea comes from that the speed of light is a limit that you can't cross. But this argument has some issues. The first issue is that it doesn't mean faster than light travel is forbidden in Einstein's theory. Indeed, his theory is entirely compatible with faster than light travel. The problem seems to be instead that you can't accelerate from below the speed of light to above the speed of light. It's more like a barrier than a limit. The second issue is more a peculiarity. It's that on all other occasions, when physicists see some quantity go to infinity, they'll tell you that infinity is unphysical and a sign that the mass doesn't properly work. Big Bang, black holes, non-minimalizable effective field theory, whatever. If there's a singularity, they'll say it's a mathematical artifact and not real. They don't say that in this case, and I think they should. The third issue is that we have a counterexample to the claim that one needs an infinite amount of energy to reach the speed of light, which makes the argument extremely suspect. But to see why I say this, I first need to tell you where mass comes from. No, it's not too much cheese, it's simpler than that. Most of the mass of objects around you isn't really mass, it's binding energy. You see, almost the entire mass of atoms is in the nucleus. The nucleus is made of neutrons and protons, and the neutrons and protons are each made of 3 quarks. For the neutrons, that's 2 down and 1 up, and for the protons, it's 2 up and 1 down. Quarks, not thons, I mean. The quarks do have masses, but if you add them together, the sum is far less than the mass of either the neutron or the proton. Instead, most of the mass of neutrons and protons is the binding energy from the strong nuclear force that holds them together. We interpret it as mass because E equals mc square, but this means it's really odd to put the mass of an object into this equation in Einstein's theory, because really, if you look at the object microscopically, most of it isn't mass. And yes, that means most of you isn't mass either. You're almost entirely made of pure energy, though when I see how much time you spent watching YouTube, I find that hard to believe. What's with the remaining mass, the part that isn't binding energy? Electrons and quarks do have masses, albeit very small ones. These masses come from the Higgs field, not to be confused with the Higgs boson. To be more precise, the masses come from the condensed Higgs field. This Higgs field condensate fills the entire universe and drags on particles. It's kind of like the 19th century ether, but with 2 important differences. First, the ether was believed to be necessary for light to travel, but for the Higgs field, it's the opposite. The particles of light, the photons, are massless, which means they don't feel the Higgs field at all. But other particles do feel it. When the field condenses, it sticks to the particles. That slows them down, and to us it looks like they have mass. Another difference between the condensed Higgs field and the ether is that the Higgs condensate looks the same for everyone, regardless of how fast they move. It's just a number at each point in space-time, and everyone agrees on what this number is. It's like the number of socks in your washing machine. Doesn't matter how fast the spin cycle is, the number of socks doesn't change. Or if it does, I guess it's time for new socks. The ether, on the other hand, was believed to be basically like a fluid. Some people would drift with the flow, and some people would move against it, and they'd see different things. This is not the case for the Higgs field and its condensate. If you like technical terms, and I just know you do, it's a Lorentz scalar and invariant under Poincare transformations. Okay, so the masses of fundamental particles come from the Higgs field. But this is only the case when the field is condensed, and that wasn't the case in the early universe. Think of an early morning in spring. No, not the coffee. I mean the dew on the grass. Where does it come from? Well, air contains water vapor, which means that individual water molecules float around in the air, but warm air can hold more water vapor than cold air. If the air temperature drops during the night, the water molecules collect to form drops, which are too heavy to keep floating, and they fall to the ground. The Higgs field has done a very similar thing, not in the early morning, but in the early universe. In the early universe, it was really hot. There was a Higgs field, but it wasn't condensed, kind of like the water vapor in the air. But then the temperature dropped, and the Higgs field condensed. This condensate now fills the entire universe, but it was only when the Higgs field condensed that particles acquired masses. It's a phase transition called electroweak symmetry breaking, and it's believed to have happened at about 10 to the minus 10 seconds after the Big Bang, at a temperature of 10 to the 15 Kelvin. That's much hotter than even the center of the sun. What all this means is that in the early universe, none of the particles had masses. They were all massless, and they were all moving with the speed of light. Later, they were not. And here's the important bit. The energy that was released in this phase transition was finite. If it hadn't been, we wouldn't be here, and someone would have written a paper about that, I'm sure. But the equation that we looked at earlier said that the difference in energy should have been infinite. What gives? Mathematically, it's pretty obvious what goes wrong with the earlier argument. If you look at this equation again, you see that if this factor goes to 0, but the mass also goes to 0, then the ratio can well remain finite. This doesn't help us at all to travel at the speed of light, because we can't just uncondense the Higgs field. Even if we could, it'd basically evaporate the traveler, and I mean, I'm not a doctor, but that's probably not healthy. So this isn't going to let us build a warp drive. But it shows that the argument that the speed of light is a barrier isn't even technically correct. There is another reason that physicists often bring up for why you can't travel faster than the speed of light, which is that it can allegedly cause time travel paradoxes. The argument goes like this. Suppose Alice observes a spaceship, which goes by faster than the speed of light. Zoom, here it goes. Her friend Bob can't afford the new super-duper spaceship and lamely zooms by in last year's model at merely 90% the speed of light. Then Bob would see the spaceship going back in time. Let's draw this into a space-time diagram to see why. The horizontal axis depicts one direction of space, so left and right, for example, and the vertical axis is time. A spaceship which doesn't move according to this axis just makes a vertical line. A spaceship at constant velocity is a line which has some angle to the horizontal. By convention, a 45-degree angle is the speed of light. Alice just sits there and moves on this straight line, and everything that happens on a perfectly horizontal line happens simultaneously according to Alice. The faster-than-light spaceship goes by like this, and Bob moves on this line. The question is now what Bob sees. For this, let's look at 2 particular events, and let's make sure those events have a clear error error of time from entropy increase. Let's say someone drops a raw egg. The guy in the spaceship stumbles here, and the egg smashes to the ground here. This means, importantly, that time on the spaceship passes in this direction and not in the other direction. Since Bob is moving relative to Alice, he sees different events happen simultaneously. I explained this previously in my video on why the past still exists. So, well, either take my word for it or watch the other video. For Bob, events that happen at equal times are on these straight lines, not on horizontal lines. You can then see that for Bob, the order of events is that the egg first smashes to the ground and then gets dropped. It seems that for Bob, the time order on the faster than light ship is reversed. Crazy. The first reaction you may have to this is, who cares what Bob sees? I mean, you can watch this video in reverse, and that doesn't mean I actually spoke in reverse. Fair enough. The second reaction is to point out that this isn't what either Alice or Bob see anyway. You can't see a faster than light ship coming for the same reason you can't hear a supersonic plane coming. What do you want to see it with? Instead, both Alice and Bob will only see the spaceship after it's gone by, and then they'll see it moving away in both directions. And again, you can say, so what? I mean, gravitational lensing distorts galaxies into rings, all right, but that doesn't mean the galaxy is a ring. It's just some weird trick on our perception. And that's entirely correct. But physicists have noticed that too. Thing is, this wasn't the entire argument.